Hi, welcome back. So another data analysis video. So in the previous video I demonstrated how to conduct one-way ANOVA using different software libraries in Python. We use stats models and we also use SciPy to conduct that. So what I'm gonna do in this video is a quick demonstration just to follow up on that with an example using an imported data set. So in the last video I kind of generated some data, and we conducted a one-way ANOVA on that. In this video I'll import some data and we'll do a similar sort of thing and some post-hoc tests. So this is actual existing data we're going to use in this case. So if you remember, when we conduct an ANOVA we are comparing the mean scores on different groups. So our independent variables are categorical grouping variable, and we're looking at differences in mean scores on a scale dependent variable. Okay, so let me just import some software libraries that we might need. We're going to import pandas as PD, numpy as np, scipy.stats as stats, matplotlib.pyplot as plt, seaborn as sns, and the data. So those are the usual nicknames, handles that we use to abbreviate those different software libraries. And then I'm going to import some data looking at it. It's basically from a lie detector study where people were told to lie, tell the truth, or complete some sort of control task, and they look to see differences in heart rate. So it's like the dependent variable was their heart rate, so their level of heart rate, and the independent variable, different groups, were whether they were lying, whether they were telling the truth, whether they were just doing some control task. So this is data that was actually recorded by some of my colleagues, and technically, well, in truth, this was kind of repeated measures design there. The same people lied some of the time, told the truth some of the time, didn't control. But for this video, we're going to treat this as an independent groups design where one bunch of participants were in a condition where they lied, another bunch were in a condition where they told the truth, just for illustration purposes. And then later on, I'll probably use a similar example when we do a repeated measures ANOVA in a different video. So what I've done is I've imported this data set using the pandas read_CSV method. The data set's called HR polygraph, and it's saved as a CSV file on my computer. So HR standing for heart rate. And what you can see is these scores are kind of like arousal measures of heart rate, and the column headers are the different conditions. So what I'm going to do is I'm going to create a groups object with the three variables that we're interested in. So there's another variable there, framing. There were different framing conditions for this particular study, but we're not interested in that particularly at the moment. So I'm going to create this object called groups, where we're just going to extract the three variables that we're interested in, or the three conditions, three groups that we're interested in: lie, truth, and colored square being a control task. And if you look at the data type, those three, they're all shown as float 64, so they're all decimals, floating point numbers. So let's run this using the SciPy stats f one-way method. Okay, so I'm going to create a data frame object, or a new object called AOV_res. So ANOVA results is just an abbreviation for that. I made that up. It's not particularly mean anything in terms of coding or syntax. And then that object, we're going to set that equal to, we're going to use the stats.f_one-way method. And all I've done here, you can see, is pass from the groups object we created the three different columns, or the three different variables, features of interest. And then I've specified the print to give us a return or print out the results underneath. And as we've seen in the previous video, it returns the F statistic, the F result for ANOVA, and it returns a p-value. So what we're seeing here is we've got an F statistic of 3.09 and a p-value of 0.04. So it's statistically significant if we take a significance threshold, an alpha criterion of 0.05, which is quite common in a lot of disciplines like psychology. What I did there, I kind of ran that. I created a new data frame object. extracting the groups of interest, and we just passed each of those variables in that new groups data frame object in as the parameters, the three groups to compare essentially. Hopefully that's clear the way I've done that. But let's do the same thing again, but we could have just done that directly from the original data frame. And what I'm going to do here is I'm going to ask it, rather than just one object, I'm going to ask it to return two things, f value and the p value. It does that anyway by default, whatever we specify here. But I'm specifying f value comma p value. Then we're using stats f underscore one way again, and all I'm doing here is I'm passing the groups as the original data frame. We called it hr underscore df. That was the object it was saved as. So heart rate data frame. First group's lie, second group's truth, third group is the control colored squares condition. And then I'm just using a print statement to format the output here. So I'm creating a string saying f value, and then we're going to print the f value that's returned by our analysis, and then p value, and we're going to return the p value. Let's run that, and you can see we get exactly the same result as above because we've run the same test. I've just set it up slightly different and formatted it slightly different so it looks how I would like it to look. Okay, so we've got a significant ANOVA result, and as a consequence we've got three groups. We need to do post-hoc tests to find which levels of the independent grouping variable have significantly different means from each other. Sorry, I'm just going to correct a typo. There we go. So we're looking to see, so of the three groups we've got, lie, truth, colored squares. What we want to know is, do the lie and truth groups significantly differ in terms of their means? Do the lie and the colored squares group significantly different? And do the truth and the colored squares group significantly differ? So we're making multiple comparisons. So we want to adjust in some way, make some sort of adjustment correction, so we're not committing a typo error. So in order to do this, there are multiple different post-hoc comparison tests we could use, and I think there are more than like 18, and there are books written about them. And what I'm going to do in this video is demonstrate how to use the Tukey HSD. I used it in the same one in the previous video, and I imported it from the multi-comp kind of library catalog of tests that are available in the stats models library. So what I'm going to do is I'm going to use a from statement. So from stats models.stats.multicomp import pairwise Tukey HSD. So we're in this cell here, we're going to import a particular post-hoc test method to use on our above data. But the data is in short and wide format with the three categories saved as three separate variables. In order to use this method, it kind of works better if I convert it to a long and thin data frame in order to run the pairwise comparisons. And we can do that using the pandas melt method. So hopefully you can see what that means. I mean, these measures all measure the same thing, arousal, these numbers, but it's separated. It's in what's called short and wide format. So they're split over three categories or three columns, and when you have it in this format, it doesn't tell you what these measures relate to really. So I prefer to have data in long and thin format. But that's what we're going to do here in this cell. Is we're going to use the pandas melt method to create a long and thin version of the data set, and what that will give us is a column which has got it's got a categorical variable which has lie, truth and colored squares in it, and our DV, which will give the name mean arousal, because that is what it actually relates to. So to do that, I'm going to create a couple of lists, a couple of objects. I'm going to create something called cat_con, so categorical condition, and then I'm using this list function. I'm just saying, and pass it, what I'm saying is groups, the groups to use, groups.columns, use the column names as the groups. And then I'm going to then create this groups long, so long format data frame. And to do that, I'm using pd pandas.melt method, and we're passing in groups, which was the object we created above. The value variable is going to be a categorical condition here, so the 3 groups. The value name is going to be mean arousal, and we're going to ask it to ignore the ignore index equals true, so it's going to ignore the index in the original data frame. Otherwise, what we'll get is kind of 1 to 8, 0 to 79 repeated 3 times. But we're pretending these are independence groups. So if I run that, you can see what it's done is created, it's called a variable essentially, and it's created a variable with 3 categories: lie, truth, and colored squares. And then the actual values that are recorded are now saved as mean arousal. So this is kind of more meaningful format. It's a better format for us to use for the Tukey HSD using stats models. You can see the difference there between this and this data frame. Same information, just formatted differently. Okay, so if we look at the data types, what we'll see is our kind of categorical variable is an object, which it should be, and a mean arousal is still a floating point number, so it's a decimal, saved as a decimal. Okay, so let's run this pairwise comparison using the Tukey HSD method, and we're going to specify some in the parentheses a number of parameters. NDodge relates to the dependent variable, data variable. Groups is going to be the grouping variable. A couple of type errors there. And alpha is our significance criterion. So what you can see here, I've created this object called Tukey tests, Tukey_tests. We're using the pairwise_Tukey HSD method from stats models. Our DV, labeled as NDodge, is going to be groups long. So we're taking it from this groups long data frame object, and it's mean arousal, so it's these scores. And our groups are going to be the variable from groups long. It gave it the label variable because we didn't specify anything else, and that's just the different categories. All right, let's run that, and then I'm going to just call I'm using Tukey test.summary, and we'll get the output. Oh, I ran the wrong cell, the same cell twice. Never mind. There we go. Okay, and if you've seen the previous video, you'll know that I kind of like this type of post-hoc testing using stats models. It shows us the groups it's comparing. It gives us an adjusted p-value so we can assess whether this is significant at the 0.05 level. So it's adjusted that. And it tells us, it's got this reject column that tells us whether or not whether it's true or false that we can reject the null hypothesis that there's no difference between the 2 groups. And what we're seeing here is that the only one of these 3, lie and truth, have a p-value of 0.04, so they're statistically significantly different. So it tells us it's true that we can reject the null hypothesis. The other 2 are shown as false, and you can see that from the p-values above. Okay, so let's just look at some of the information, just some descriptives there. What we could do, what we possibly might like to, I haven't obtained it, but we could obtain descriptive statistics for each of the groups individually, so we know what the means are, and we'd maybe want to report the mean for each group, so you can, and then the results of the test, so we can see how they differ significantly. Just to finish this off, so we can visualize this. So what we've found is we've got a significant F-test. And when we've looked, there are only 2 groups that are significantly different from each other, and that's arousal in the lie and the truth condition. And a forest plot will help us visualize that. I've also called the Tukey, I've used like the Tukey test summary again. I could have missed that off and just obtained the plot, but there you go. You're able to see the 2 together. Lie and truth are the only ones that are significantly different, and you can see truth and lie don't overlap. The error bars do not overlap at all. I put this vertical red line in so you can see that. Coloured square and lie overlap, so that's significantly different, and same with truth and coloured square. But these 2 differ significantly. That's what was driving the significant difference. And what we're seeing here, what it's telling us, we can see here from the mean scores on the x-axis, that mean arousal was significantly higher in the lie condition compared to the truth condition. Okay, hopefully this was useful. and interesting. That was just there. It was just to kind of reiterate what I did in the previous video. A one-way ANOVA example, but this time using kind of a real data set rather than a simulated data set. Okay, so I think I will continue with a bit more ANOVA, a repeated measures one, and we'll go on to some more complex designs in the next few videos. Thank you for listening.